So, this is the engine. I'd like to call this the test stand, and this right here is the actual engine itself. Everything else is just sort of like a supporting subsystem. The engine consists mainly of a turbocharger, which happens to be 2/3 of a jet engine. It's a compressor, which is driven by a turbine. All that's missing is the combustion chamber, which is what I've had to fabricate. The air gets sucked in, compressed, comes down this feed tube into the combustion chamber, which consists of an outer housing and a smaller flame tube, and this tube actually runs the entire length of this housing. And the only way for the air to go from the gap between them into the flame tube where the flame exists, that's why it's called the flame tube, is there's a series of holes which are strategically sized, placed, and counted to control the airflow and how the air is being introduced to the fuel to ensure that you get a nice, sustained, complete, and steady burn. You don't have any combustion instability or anything like that. So the fuel is, of course, introduced in this end. You've got the first primary row of holes, you've got the secondary holes, and the tertiary holes. The burning starts with the air introduced at the primary holes. There are a lot of small holes for the primary holes. That's to introduce a bunch of turbulence. And they consist of about 30% of the total hole area. With the total hole area is just the area of the inducer, of the compressor. So 30% of the total area of the holes, and that's so that just to give it enough oxygen to sort of get the burn going, but not any more than that, otherwise you'll blow the flame out, essentially. The secondary holes give it another 20%, and that's just to burn the rest of the fuel that wasn't burnt from the first 30% in the primary. And then the last row, the tertiary holes, there are even less, even bigger holes. So there's only about 6 holes here, as opposed to 16 down at this end. There's only 6 holes here. They're really big, and they dump in another 50% of the oxygen simply to cool the reaction before it hits the turbine. Let's talk about supporting subsystems. The most important one is going to be the oil system. Turbo needs an oil for multiple reasons: to cool the shaft, to lubricate the shaft, and in this case, because of diurnal bearing, it also needs to control the dynamics of the shaft. We'll talk about that in a second. So, oil tank, we've got 2 oil pumps, which are actually just inline fuel pumps. They're the same one I'm using over there for the kerosene. Originally, it only had 1, but I found that wasn't enough to, it wasn't a high enough flow rate. So I'm running 2 in parallel now. They tee together, they come to the oil filter, which is, of course, very important. You don't want any foreign objects fouling up your shaft. It comes up here, and it can either go up the feed line or it can go through the bypass. I've got a valve here to control how much goes through the bypass, and this effectively allows me to control the oil pressure. Anyway, coming up the feed line, we've got an oil pressure tap, which goes to the gauge, and then this feeds directly into the turbo. You'll notice that this is metal, and this is nylon, and this is just a rubber hose with a braided metal lining. This is all metal. It has to be, because it's close to the turbine housing, which will get very hot, and you don't want anything except metal near that turbine housing. Coming out the bottom, this is the drain line, drains right back into the oil tank. I'm not going to go over this into the nitty-gritty of everything. If you want to know about turbocharger oil, let's say requirements, just Google turbocharger oil requirements. There's a lot of good info for manufacturers and even on forums about how to properly set up a turbo lubrication system, because people use them in cars all the time, and it's important knowledge that you might need to know. So if you want to know about that, I just say Google it. There's a good paper from Precision Turbo that details exactly how you need to set everything up. Coming around, we've got the gauges. We've got oil pressure, which is tapped off here. Boost pressure, which is tapped off here. And this is important because this boost pressure is about the only way that you know how hard the engine is running, since there's no tachometer on this. The only way to measure the RPM of the shaft would be to use a visual tachometer, or a frequency counter, as they are sometimes called. And that's complicated to set up and calibrate. So, oil temperature here, which we've got a probe in the oil tank there. And this is exhaust gas temperature, which is probed here. And I don't have good lighting over here, so I'm going to have to turn it around to show you what's going on back here. Normally, there'd be a jet pipe here, which would accelerate the exhaust gases. I haven't made one of those yet. And this probe would be in the jet pipe. This is actually just a thermocouple, but I'm calling it a probe. Right now, since I don't have a jet pipe, I just have this sort of mounted on this spare piece of metal. That's and now it sits in the exhaust gas stream, so it's good enough. Anyway, coming back to the other side, let's talk fuel. So originally this was meant to run on propane, because that just solves a lot of problems. It's already gaseous, it's already pressurized, so you don't have to worry about vaporization. It's very forgiving in terms of the fuel-air mixture that it will burn at. But I found during initial tests that you simply can't feed this thing enough fuel with propane. I would have had to tee like 2 or 3 propane tanks together in order to run enough propane to get this to keep this thing going. And that's just impractical. So I upgraded it to run on kerosene. And this is the propane line. This is the propane line. It, of course, feeds propane in. Originally, the propane line was up in the center, and that's now reserved for the kerosene. So this comes from the tank. Got a solenoid valve, sort of like an emergency shutoff valve or safety valve, to ensure that in case electricity were to be lost or something were to happen, like the switch were to accidentally get turned off to the oil pumps, it would immediately cut off the gas and not run the engine inadvertently without oil pressure, because that would very quickly destroy the turbo. Here is a needle valve for fine control of propane, and then of course goes up into the flame tube. The propane sprays outward, like from the side it sprays outward radially and not down the length of it. And that's to ensure that, again, you want nice, good mixing of the propane as to not have a flame out. Now, like I said, propane wasn't enough, so upgraded it to kerosene. So, it's a kerosene pump. It draws kerosene out of right now I'm just using a 5-gallon jug of fuel-grade kerosene. Comes up into here. I'm using a similar system to control the fuel flow with as a bypass system as I'm using to control the oil pressure and the oil flow. So this just goes right back to the kerosene tank, and then teeing off this way, this goes into the combustion chamber. On the other side of this, there I have a misting nozzle, which you might find in an irrigation system in a greenhouse, for example. It's a hollow cone. It atomizes the kerosene, and the kerosene sprays out in an 80-degree cone that intersects with the primary holes. So, and that's to ensure that the kerosene never actually touches any metal and can build up anywhere. So what happens is, as the kerosene sprays outward, instead of just hitting the side of the combustion chamber, it gets blown back in by the air rushing into the primary holes, and, well, at that point it would be burning, because now there's oxygen for it, which it can use to burn. So, the reason I still have the propane hooked up is because propane is much easier to get lit, and it won't build up if it doesn't light immediately. So as long as you're blowing air through this, you can fill this thing up with propane. You can just blow it out, and you don't ever start this thing with it stagnant. You always apply well, I'm using a leaf blower to start it, so you always apply the blower to run air through it before you introduce any fuel. So the propane can never build up because it will get blown out as fast as it gets put in. If you were to try and start it just on pure kerosene, one, it's a lot more difficult to get lit, and two, if you don't get it lit right away, it'll just build up inside here, and then when it does light, you'll end up with a runaway start because there's now suddenly a whole bunch of kerosene burning, and there's more kerosene burning than you were intending to burn, and that's really bad. So you can think of the propane as the starter or the pilot light, you might say. Anyway, moving on to ignition. Using a simple spark plug for that, just screwed right into the end of the combustion chamber. This is the wire which feeds electricity. This is a ground wire. For ignition, turns out that these things exist. Now, what is this thing? This is, I don't really know what it's called, but if you Google high voltage pulse generator, you'll find them everywhere. And this takes a 12 volt DC input, and then generates an 80 kilovolt voltage difference across these two wires. So all I've done is, and I know these colors are backwards, but I don't actually know which is high and which is low anyway. Not that it matters. So you feed one end into the spark plug. Of course, the spark plug, it's got a spark, there's a gap, and then it's ground to the threads, and then the current travels back through to this wire here. And that's a lot simpler than having an automotive ignition coil with a relay to generate a pulse and a capacitor to control the pulse frequency. It's just way simpler and lighter and easier. The last thing is electricity. Right now this is all being run off of a simple 12 volt battery, wet cell. This is all a big mess. It's rather complicated. I'm not going to run through it all, but that's that. Everything here runs off, everything that is powered by electricity, i.e. the pumps and the solenoid valve and these two gauges, are all powered just off the battery. I've got it wired up in such a fashion that this is ignition, this button. This is sort of like a master on. This controls power to the solenoid valve, which is normally closed, so that means it will close when it runs off when there's no power. So this will not open until this switch is flipped. And then this switch, and this also turns on the oil pumps. And then this switch will not operate unless this switch is on, so this switch also supplies the power to this switch. This switch, when turned on, will turn on the fuel pump, and these two gauges. So I've got this wired in such a fashion that no fuel, propane or kerosene, will be entering the combustion chamber if there's oil pumps are not on. That was the whole purpose of wiring it in such that fashion. If this switch got turned off by accident, or if the electricity died, or if this switch died, or something like that happened, or maybe an electrical connection came loose from this switch, it would immediately kill power to all the fuel, so that you're not running the turbo without any oil. That would be really bad. So that's that. This is I wrote down like a quick start checklist so I don't miss any steps when I'm starting it up. So that is my DIY turbojet engine. Hope you like it. I don't know if I'm going to include it in the same video. I might cut it together, but later I'm going to do some testing, and I'll just show it off so you'll get to see it in action. And I'll catch you later.